So now that we have some appreciation for the solenoid, what its field looks like, let's do Ampere's law for the solenoid. Okay. Now this solenoid, we need to give it some properties, so let me just draw it first. We have our loops, 8 of them, and we can have it come out on this side and in on this side. All right, and let's say it's carrying a current I. Current I is coming in and going out, steady current in the solenoid. Let's say in some length L, so it's actually a nice long solenoid, but let's say in some length L, there are N turns, big N turns. Just to give us some idea of the density of the turns in the solenoid. Okay, so in Ampere's law, what we got to do is draw an Amperian loop. Okay, so we're going to draw one that's inside the solenoid and covers the length L and then goes outside the solenoid, like that. Okay, and we're going to do what we always do when we're doing our nice symmetric vector calculus. We take the integral and turn it into several terms, one for each side of this Amperian rectangle here. And we say, okay, we know the real thing we're looking for is the integral of b dot ds equals mu naught I. So this integral is around a closed loop. We're going to break it up into 4 integrals, one for each piece. Okay, so first let's do number 1. So the integral, I'll just put a 1 there, along path 1, of b dot ds plus, well, I'll just write them all, integral of 2 b dot ds plus integral path 3 b dot ds plus integral of path 4 b dot ds. Okay, let's figure out what all these things are. So the integral of path 1. So I'm not even going to make you assume that the B field is constant all the way inside the solenoid. I'm just going to say we know that it's going to go this way. We know it's going to uniformly point in this direction. So if we march ds along the path that way, then B is always parallel to ds. The answer to this is basically B times L. If we just assume B is constant when you go this way, we go distance L, this is BL. Okay. The second one, 2, is going this way. We know that the B field has to be this way because of the way the current loops make a field. So this one is at 90 degrees to the B field when you're inside, and the B field is very small, essentially 0 when you're outside. So this one is 0. Okay. B3 is down here, and as you march your DS's this way, there's no B field. The B is very weak on the outside, so this one is 0. And then finally, we come marching in here, out here, there's essentially nothing, no B field, and when you get in, there's a B field, but it's perpendicular to the DS's, so 0. So all the terms are 0, except B1, only the term when you go along the inside of the solenoid. Okay, so let's see. Oh, except, let's see. So let's say BL equals mu naught, but how much current is going through here? Oh, it's not just I. The current I flows through every turn of the wire, right? The total current in this loop is some number of turns times I, right? So BL mu naught, it must be in the total number of turns in this length L would be the total current. Right? So now we can then say, then the B field inside the toroid is mu naught big N over L I. So it only depends on the permeability of free space, the current, the current in the solenoid, the number of turns per unit length, the density of turns. Well, actually, we often give that its own little variable. We call that little n. So the answer usually you'll see is mu naught little n I. Often in physics, a little windy. Often in physics, we use the big number to tell you the big capital letter to tell you the absolute number of something, and we use the little letter to tell you the number per unit length of something. So what this tells us, though, the interesting part, is that we have a number for the B field now, mu naught number of turns per unit length times I, but also it doesn't depend on where you are in the solenoid. Nothing we did ever said if you're in the center or near the edge, and what Ampere's law is telling you is that the B field is uniform as you move around in the solenoid. It always points up, and it's the same magnitude here, as it is here, as it is here, as it is here. Even though that magnitude changes in a single loop in the solenoid, it all becomes equal. And you can kind of see it in terms of field lines. All those field lines are going to distribute evenly inside the solenoid.